Hi everyone, my name is Jerome Bellegarda and I'm Distinguished Scientist at IEEE. In this video, I'd like to give a brief overview of a paper entitled Multilingual Transliteration for Pan-Indic Keyboard Input, presented at ICASSP 2024. This is work done at Apple before joining IEEE, where we looked at Indic transliteration and more particularly at how to avoid manual switching between monolingual keyboard. I'd like to acknowledge the contributions of my former Apple colleague Bishal Barman, with whom I had many productive discussions over the course of this work. So let's begin with a brief overview of Indic languages. India is home to several hundred languages, with over 30 of them spoken by over 1 million speakers. Of those, the Indian Constitution recognizes 22 different regional languages, part of a specific list of so-called scheduled languages. They mostly come from two language families, Indo-Aryan in the north and Dravidian in the south. In addition, English is in widespread use for official purposes, since no single Indic language has status of national language. Further complicating the situation, there are many different scripts in active use throughout India. Nominally, every native script requires a separate keyboard, which is a major challenge when communicating across the country. As a result, many Indic speakers, especially those familiar with English, prefer to enter text in phonetic style using the Latin script. This so-called transliteration process allows a single QWERTY keyboard to serve as input for multiple languages. Users activate a mapping dedicated to one of the desired target languages, and the output simply gets mapped to the associated native script. Unfortunately, for multilingual users who routinely communicate in several languages, such manual language switching does not lead to the best user experience, which motivates the search for a multilingual mapping by design. To get started, let's first briefly review monolingual Indic transliteration. The underlying framework is based on the kind of end-to-end encoder-decoder architecture commonly used in neural machine translation, where a sequence-to-sequence model maps an input sequence in language A to an output sentence in language B. For example, in the case of English to French translation shown here, the tags A and B refer to English and French respectively. Now, transliteration works in a similar way, except that it is done between two scripts instead of two languages. So, in transliteration, the model maps an input sequence of Latin characters to an output sequence of native script tokens. Processing is typically done word by word, so users do not have to wait for the entire sentence before seeing the results. This is illustrated on this slide for the input character sequence NAAM, which results in the Hindi word for name. In this case, the output tag would specify Hindi as the desired native script, making the mapping specific to the target language Hindi. What we would like to do is remove those tags to accommodate outputs in multiple languages. But of course, if we do that, the problem becomes more difficult because the model now has to guess what the target language may be. Since that guess has to be made based on context, it is now beneficial to process every word on the basis of the entire sentence history, so the output is a word sequence as opposed to a single word. This allows the conversion to be informed by a stronger internal language model. Additionally, if external information is available, be it in the form of specific orthographic constraints or knowledge of the general interaction context, that could be useful to prevent illegal sequences from being generated, and we'll say a little bit more about that later on. The end result is a tagless, multi-word transliteration model that can accommodate multiple languages. This approach has a number of benefits that make it especially attractive to tackle Indic languages. For one thing, training the model across multiple languages opens up the possibility of exploiting similarities across languages. Here, for example, the input character sequences NAAM and PERU occur in multiple languages, all of which can be associated with the English word name. So, tagless transliteration creates opportunities for cross-lingual learning. In addition, keeping track of the sentence history is a natural solution to leverage a stronger internal language model. Here, the input character sequences in yellow occur in multiple languages, but by looking at a multi-word context, it is straightforward to transliterate to the correct language. So, multi-word processing creates opportunities for multilingual disambiguation as well. The question then is whether exploiting such opportunities is a viable approach to replace separate, language-specific transliteration keyboards. To answer that question, we trained a tagless multilingual transliteration model on both single-word and multi-word parallel data, as described in this table, and compared it to the baseline monolingual models. We wanted to know, in particular, whether it is possible to maintain approximately the same level of monolingual accuracy while offering additional multilingual capabilities at the same time. And those are the results we observed for the keyboard input case. We used two different evaluation metrics. The conversion error rate measures how many times the model corrects away from intended input by suggesting a spurious candidate. And the recovery error rate quantifies resilience to different types of common mistakes in intended input. Both figures of merit show a small but consistent improvement across all three languages considered, which validates the proposed multilingual strategy. Note that the results we've just seen did not use any external information, so conceivably they could be even better where some is available. For example, linguistic knowledge may be available in the form of orthographic constraints, which could help avoid generating the kind of spurious suggestions mentioned here. It may also be possible to exploit non-linguistic information coming from the larger context in which transliteration takes place. For example, the user may be known from history to prefer a particular language when communicating with a given recipient. In that case, spurious token candidates in another language can be safely filtered out. To summarize the key takeaways, we looked into Pan-Indic transliteration with the goal of unifying text input across multiple Indic languages with different scripts. The main motivation was to obviate manual switching between monolingual keyboards. We proposed a multilingual framework which is tagless and multi-word to both exploit similarities and resolve ambiguities across languages. And we observed in experiment comparing monolingual and multilingual transliteration that this framework is viable to help multilingual users enter Indic text faster and more accurately. This is especially true when external information is available to reduce the likelihood of incongruous suggestions, either in terms of incorrect word sequence or wrong output language. Okay, we've come to the end of this presentation. If you have any questions on any aspect of the paper, feel free to drop me an email at the address shown here. Thanks very much for watching.